this test, which will be 2 weeks from Friday on the 14th, yes, 14th, will be on chapter 6 and 7. And remember, I don't see you this Friday. And I don't have office hours Thursday or Friday. Yeah.
Did you mean the test or the quiz?
We have a test. Did I say quiz?
I don't know.
We have a test on the 14th. We have a quiz next Friday. Yeah. And on Wednesday, I'll let you know what's going to be on that quiz. Today, we're going to talk about balancing equations. Some of you learned this in high school. It's always good to review. And there's some things that I'd like to talk about in terms of how to go about that. We're also going to talk about phase labels. And I didn't get to talk a whole lot about solubility ions and electrolytes in my class last night, but we'll do what we can. Everybody good? Okay. So we have a number of rules for balancing these equations. Rule number 1 is only balance with coefficients after all compound subscripts are correct. And I will talk about what I mean by that. For example, if I have MgF2, I'm going to write out my compound so that it's, if it's an ionic compound, I'm going to write it out so that it is a neutral charge balanced ionic compound. So right now we have how many magnesiums and how many fluorines? 2. Okay. So this is the subscript. So I want all of these subscripts in your compounds correct before, for example, you add this. This is your coefficient. So the numbers you use to balance your overall reaction that go in front of the compound, those are your coefficients. And what does that mean in terms of the number of atoms? What does it apply to? Everything, that whole compound. So how many magnesiums do we have? How many fluorines do we have? Exactly, okay? So we want to make sure that we have this, and then when you've done that when you have the correct neutral balance, the whole equation, then you can add in your coefficients and work out how to balance the overall reaction. So if I give you a problem like this, sodium chloride reacts with magnesium oxide to form sodium oxide and magnesium chloride. I might ask you to write out this reaction in terms of your compound. Okay, so this is the word. And there are some key words that you need to know. First of all, reacts with. Okay? That means you are adding sodium chloride and magnesium oxide. And so what's the formula for sodium chloride? Plus, what's the formula for magnesium oxide? What was that? MgO, because magnesium is 2 plus and oxide is 2 minus. Okay, so you've balanced those. What does 2,4 mean? Like, how would you draw that out? An arrow, exactly. Sodium oxide. Now, how are we going to make a neutral compound that's sodium oxide? Yeah. So what's the charge on sodium? +1. What's the charge on oxide? -2. So how many sodiums do I need? Na2O. And I am not concerned right now that I have 1 sodium and 2 sodiums on this side. Don't worry about it yet. That's what the coefficients come in for later. This is why we're just doing our neutral compounds. And then we will figure out the balancing later. Now, what is the formula for magnesium chloride? Because and means it's another product. So what is magnesium chloride? MgCl2, nice. So what are these? What are they called? Reactants. And what are those? Products, there you go. So if I say something and something produce, that's the arrow. So yeah, reactants and products. So now we have all charged balanced compounds. Now we have to balance the number of each element. So how can we do that? How many sodiums do we have on this side? We have 1 here. We need 2. So I'm going to put a 2 right here. Now, so there are 2 sodiums, 2 sodiums, 2 chlorines, 2 chlorines, 1 magnesium, 1 oxygen. We are good. Okay, so I didn't worry about the number of sodiums while I was charge balancing. I just went back and fixed it with my coefficient. Okay, and that's what I wanted you to do. Subscripts before coefficients. All right? Any questions thus far? Okay. Only slightly better. So rule number 2 is actually one of the most fundamental rules, and that's that you want the same number of each element on each side. Okay, so rule number 2. That's really the whole point of balancing reactions. Can anyone tell me why we need to balance reactions? Like, why do we need the same amount of elements on each side? Yeah. Sorry, what? Not quite. Yeah. Yes, conservation of materials, conservation of mass. You're not gonna just like put in some sodium and then it's gonna, unless you're doing nuclear fusion or fission. Sodium, if you put it in, it's gonna come out as sodium, just maybe in a different compound. okay? So the amount with all of the reactions we're doing, you're gonna want the same amount of each element on both sides. What goes in must come out. Rule number 3 is that you want to start left to right, but leave lone elements to last. This is more of a guideline, and the reason, but it will help you because it will make it easier for you to balance things. So I always like to just start left to right, like we did in our last reaction, but I leave any lone elements like carbon or H2 to the end. So H2 is still by itself, even though there's 2 H's, because it's a lone element, okay? So leave that to the end. It will make your life much easier. So if you have carbon plus SiO2 goes to SiC plus CO. Based on this rule, what are we going to start with? What element are we going to start with? Leave lone elements to last. Silicon. We're going to start with silicon. So we're going to move left to right, but we're going to skip carbon because we're going to come back to that at the end. Okay? It just makes it so you don't have to go back and forth as many times, because the easiest elements to balance are the ones that are left themselves. So balance everything else and then come back. So silicon is actually fine right now. But what about oxygen? Is it balanced? No. So we have 2 oxygens on the left and 1 on the right. So what do we need to do? I'm going to make 2 carbon monoxide. Now I had a question in yesterday's class. Why couldn't I just put a 2 on this oxygen? You don't want to change the actual composition of the molecule, okay? Carbon monoxide and carbon dioxide are 2 very different molecules. You know, yes, it's CO2 and CO. They can both kill you, but they kill you in different ways. So also, carbon dioxide is 70, no, that's nitrogen. Carbon dioxide is a large part of our atmosphere, what we breathe in. You wouldn't want carbon monoxide to be that much of our atmosphere, okay? So just know they're very different compounds. So you have to put a 2 out here. Now, let's revisit carbon. What do we need? How many carbons do we need on this side? 3. Because you need to take into account these 2 carbons and this 1 carbon, put a 3 here. So a really good way to do this, to count up a lot of people like to do this as they go along, counting up your atoms of each, write it under the reaction. So I have 3C, 1 Si, and 2 oxygens. And on this side, I have 3C, 1 Si, and 2 oxygen. And you can start out that way and change it as you go along into balance, and I'll do that on the next problem. Let me just show you why I recommend not starting with the carbon. So C plus SiO2. You'll get to the same place, but it'll just take a few more steps. Okay, so if I start with the carbon, I'm going to put, since there's 2 carbons right here, I'm going to put a 2 here. Okay, and then I go to silicon, that's fine, but then I need to add a 2 here. And then I have to go back and change this carbon to a 3. Okay, so it just adds steps. It's just easier to leave lone elements to the end. If you don't do that, you'll get to the same place, but it might take longer and it might confuse you a little. This is a relatively simple reaction. but as you go up, just leave the lone elements to the end. It will make your life easier. Rule number 4. Let me get a better 4. You don't have to write the one coefficient. So notice that here I had one SiO2 and I left it blank, okay? You don't have to put a 1 here. You can, that is fine, but you don't have to. Do not, however, put a 0 here. That is wrong. Either leave it blank or put a 1. So it would be, if you wanted to put in all of your balancing, you would do 3, 1, 1, or 2, or just do 3, blank, blank, or 2. It's like when I put Na plus instead of Na plus 1, you know that it's a 1 there, okay? So just make sure you either put a 1 there or leave it blank. Don't put an X, don't put a 0. Those are wrong, okay? Because if you put a 0 here, that means that you don't have any SiO2, which would not make sense because we have it here. So always either blank or 1 if you have only one of that compound. Okay? Let's do, oh, sorry, did everyone have that? Or do I need to go back? Okay. CH4 plus O2 goes to CO2 plus H2O. We will identify this type of reaction in next week. You will get to learn this type of reaction. You will see a lot of it, but it's like carbon and hydrogen plus oxygen goes to CO2 and H2O. Okay, it's a very common reaction. So in this case, I'm going to start counting up my atoms from the beginning. Okay, so I have 1 carbon, I have 4 hydrogens, and I have 2 oxygens on the left. And on the right, I have 1 carbon, 2 hydrogens, and 3 oxygens. Because I have to take into account both compounds that have oxygen in them. All right? So 2 from the CO2 and 1 from the H2O. What are we going to leave to last? O2. Even if I put it out front, I would still leave O2 to last because O2 is a lone element. Leave it to last. In this case, if we're working left to right, we're going to leave it to last anyway. So starting with the carbon, how are we doing on carbon? We're good. There's 1 carbon on each side, we're fine. How are we doing on the hydrogen? We have 4 on that side, 2 on that side, so we need to multiply what by 2? H2O. So now I'm going to change the numbers of how many hydrogens and oxygens I have. So now I have 4 hydrogens and 4 oxygens because I have 2 from the CO2, and I have 2 times 1, 2 more, 2 plus 2 is 4. How can I balance oxygen in this case? Put a 2O2. So I have a total of 4 oxygens. Change that. Now we're all good. Okay. We're going to do a more complicated one now. The same type of reaction with carbons and hydrogens, but I'm going to change the number of those. Okay. So we're going to do C8H18 plus O2 goes to CO2 and H2O. So write that down.
8 carbon, 18 hydrogen, 2 oxygens. 1 carbon, 2 hydrogens, 3 oxygen. All right, so our first step is we have to balance out those carbons. So let's put an 8 on the CO2. That changes both our number of oxygens and our number of carbons. So now we have 8 and we have 17 oxygens. Because we have 8 times 2, which is 16, plus 1 more on this H2O. What do we have to do to balance out the hydrogens here? Multiply what by 9? H2O. So we need 9 H2Os, which is going to change our number of H2Os to 18 and our number of oxygens to 25, because we now have 8 times 2, 16, plus 9 more, which is 25 oxygens. Can you see a problem here? What's the problem? We have 25 oxygens on this side, but we need to balance it with O2, which can only give us an even number. There are 2 ways you can do this. You can either double everything or you can use a half coefficient. Okay? So what I could do is I could say, well, if I multiply everything by 2, everything will be an even number, and I can balance it out with the O2. Okay? So I could do C2C8H18 plus O2, we're still going to balance that, goes to 16 CO2 plus 18 H2O. So now we have 16 carbons, 36 hydrogens, 2 oxygens, we still need to balance that. We have 16 carbons, 36 hydrogens, and 50 oxygens, because 16 times 2 is 32, plus 18 is 50. So, yeah. Well, now we're going to balance that O2, right? So if we have 50 oxygens here, what should we put there? 25. So turn that, now we have 50. That's option 1. Multiply everything by 2, then balance. Another option, if you don't like this whole multiplying by 2, is that you can just turn this into a half coefficient, okay? And what I mean by that is if I have C8H18 plus O2, still not balanced, 8CO2 plus 9H2O, like that, I have 25 oxygens. What can I multiply O2 by to get 25 oxygens on this side? 12.5, that's half 25. So that gives me 12.5 oxygens. I will accept either of these. Don't use half coefficients when all your coefficients are like 2, 3, and 4. Use half coefficients when you're going up to like 8, 9, 18, things like that, okay? It's gonna make your life easier. I want you to be able to see both of these because I know Catherine uses half coefficients a lot if you go into 110. So yeah, whichever works best, I will accept either. Whatever works best for you. Any questions on this? $12.5, yeah, that says 12.5. O2, I know it's a little squished. Does everybody have this down? Okay. Rule number 5. Treat polyatomic ions as one unit if they are present in both the reactants and products. Sometimes polyatomic ions are going to break up. For example, if you have KClO3, your polyatomic anion is ClO3. That can break up into KCl and O2. This is not what I'm talking about in terms of treating polyatomic ions as a single unit, because this is not present in both the reactants and products. Okay? What I'm talking about is something like, Al plus H2SO4 goes to Al2SO4 3 plus H2. In this case, SO4s are polyatomic ion. It's on both sides. You can treat that as a single unit. You don't have to count up your sulfurs and your oxygens. You can just say SO4. Okay, so let's count up our aluminums, our hydrogens, and our SO4s. Based on rule number 3, what are we going to start with? SO4, leave lone elements to last, okay? The only thing that's in a compound on both sides is SO4. So we're gonna actually start with SO4, so it'll make your life easier. So we are gonna put a 3 here. Because we have 3 SO4 on that side, we have 2 on this side, we need to multiply this by, we have 3 SO4 on this side, we have 1 on this side, we need to multiply that by 3. So that's going to change our SO4s and our H's. We now have 6 H's and 3 SO4s. So SO4's happy. Now let's go to the lone elements. Let's talk about aluminum. How's aluminum feeling? We need a 2 there because we have 2 aluminums on that side. So we're going to put a 2, and this is going to turn into a 2. And the last one we need to deal with is H. What can we do to balance out our H's? Put a 3 in front of that H2. So now we are going to have 6 H's. Questions or concerns? Yeah. You could, but I will show you an example. And the next example would be very complicated because the next example is going to have an oxyanion and it's also going to have an oxygen. So counting that all up together will be more difficult. It's much easier this way. So I'm going to give you a practice one. It's more difficult than the one we just did. And it's going to show you why this is an easier way to do it. NH43PO4 plus MgO goes to NH42O plus Mg3PO4 2. So I want you to treat, so what are your 4 things that you're going to balance? What's the first thing you're going to balance? NH4 as 1 unit. What's the second thing you're going to balance? PO4 as 1 unit. What's the third thing you're going to balance? Mg. What's the 4th thing? O. So you're taking cation, anion, since they're all present on both sides, and you're going to balance them. And this is why it would be complicated if you counted up all your O's just leave it as PO4 and oxygen. So why don't you all do that? Raise your hand if you need help. And you can always double check your work by counting up individually the oxygens and the phosphorus and the hydrogens and the nitrogens, but I would balance it this way. Oh, yeah, yes, that is, yeah. Sorry, I was so yeah, it's like fine. Mm-hmm.
So there's two amounts of the same. You can't put the two in the middle. So then you have now how many yes, so this together. Yes, exactly. So treat that as one, two. Is that too applied? Make your life a whole lot easier. So Wednesday. Yes. Wednesdays are workdays and Fridays are quizzes unless we do Tuesdays. Only if you have
You have 6
That can be,
All right. As we said, it's going to be NH4, PO4, Mg, and O. Those are the things we're going to balance. So we started out with 3 NH4s and 2 NH4s and 1 PO4 and 2 PO4s and 1 and 3 and 1 and 1. So in this case, we don't have anything by itself, so we're just going to start from the left. How am I going to balance the NH4s? We need to find the lowest common denominator. In this case, it's 6. So we're going to put a 2 here, so we can have 6 NH4, and a 3 here, so we can have 6 NH4. So a 2 and a 3, which is going to change this and this. So now we have 6 NH4. That was wrong. 6 NH4, and how many PO4s do we have now? 2. We have 2 because this 2 applies to the whole compound, and you can't put a coefficient in the middle of a compound. It has to go out front. Okay, so 2 PO4. So we have 2 there, and then on that side we have 6 NH4, and how many oxygens? 3. Because we multiplied this whole thing by 3, which means we have 6 NH4 and 3 oxygen. How's PO4 feeling? Good. PO4 is balanced. How about magnesium? We need to put a 3 here because we want to balance out that 3. So let's put 3 here. And then that gives us 3 magnesiums and 3 oxygens. Are we good? Magic. We're good. So, any questions about this?
Would you ever be given one that like doesn't work?
No, I will never give you a reaction that cannot be balanced. If it cannot be balanced, it wouldn't occur because unless it was like nuclear fission, and in that case, those are balanced too, but you have like alpha and beta particles and stuff like that. But I wouldn't give you a reaction that cannot be balanced. Another thing I remembered, it has to be the lowest ratio in your balancing should be the lowest ratio of compounds. So if this was a 4, 6, 6, and a 2, you would have to divide, if you managed to put that out front, you would have to divide everything by 2, right? We want the lowest numbers here. So if you find the lowest common denominator, if you like went too high, divide everything by whatever you need to, okay? So it should be the lowest numbers you can find. Let's do one where you have to determine the compounds and then balance it. Mm-hmm. Mm-hmm. Yeah. That's the only time that with that setup with the oxygen and the CO2 and H2O, it's a combustion reaction. We'll talk about that. But the combustion reactions are the only time that you would have a half coefficient in my class. So in that case, we had a half coefficient. In most other cases, you won't do that. But it has to be the whole thing divided by, you can't divide one side by 2 and not the other. Yeah, it has to be the whole thing. And aluminum nitrate. What is rule number 1? Subscripts before coefficients. So when you write out these reactants and products, I want you to not worry about the coefficients until you have charge balanced, made a neutral ionic compound for each of these, okay? So, there you go, get started. I will not let you forget naming. Remember your naming. That's not balanced. It'll make your balancing a whole lot harder if you don't have it. Excellent.
Don't get too worried. That's what you
There's a lot of back and forth in balancing, and that's okay. It shouldn't be like 10 times back and forth, but it's
Here we go.
How are we doing? Can I go over this? Oh. Okay, I'll give you a couple more minutes.
I can help.
Oh, we're gonna take
All right, let me go over this. What is the formula for calcium nitrate? So the charge on calcium is 2 plus. The charge on nitrate is, so it's CaNO3 2 plus. Excuse me. What's the charge on aluminum? And what's the charge on phosphate?
Oh.
Yep, so those balance each other out. 3 plus and 3 minus, boom, they're good. All right, so we already said that calcium is 2 plus and phosphate is 3 plus, so what do we have to do? 3 calciums and 2 phosphates, and finally we're going to have Al and how many nitrates? 3, because nitrate is 1 minus and Al is 3 plus. If you don't have these, it'll make your life a whole lot harder to balance it. So let's start with calcium. We have 3 on this side, we have 1 on that side, so what are we going to do? Put a 3. So now we have, okay, calcium's happy. Let's talk about nitrate. How's nitrate feeling? We have 6 nitrates here. How many do we have on that side? So we need to do 2. And let's talk about aluminum. We have 2 on that side now, so we need to put 2 here. And what about PO4? We're good. As long as you charge balance everything correctly, your balancing is actually relative. So if you have a reaction like this and you cannot, for the life of you, balance it, double check your charge balancing. All right? Let's talk about phase labels. Chris, could you please pass those out? If I put this phase label behind a compound, what does that mean? It's a gas. If I put this phase label behind a compound, it's a liquid. How about this? Solid. How about this? It's AQ. Aqueous. Can anyone tell me what aqueous means? It's an ionic compound dissolved in water. E-O-U-S. Aqueous. A-Q-U-E-O-U-S. Lots of L's. At room temperature, so at any normal temperature, an ionic compound is either going to be solid or aqueous. It's never going to be gas or liquid. So ionics are going to be these 2. Which is why you have a solubility chart in front of you, and everything on that is ionic. And Chris, it looks like we need 1 more over here. Oh, and I guess a couple more over here. So I'm going to talk a little more about solubility next class, but what you need to know now is that if something is soluble, which means it dissolves in water, is it going to be solid or aqueous? Aqueous. Soluble means it dissolves, which means it's going to be ionic dissolved in water. If it's insoluble, it's going to be what? Solid. Okay? So don't confuse solid with soluble, okay? Soluble is aqueous, insoluble is solid. So an insoluble compound, if you pour it into water, it will just sit in a clump on the bottom. It's a solid. If you have a soluble compound like salt, NaCl, or common salt, and you put that into water, it's going to dissolve, and you're not going to see it unless you oversaturate it. You're not going to see it in the water. It's going to break into its ions, and it's going to dissolve. So the way you can determine if something is soluble or insoluble is using this chart. There's one thing I want you to add in this class. We're going to consider acids soluble, okay? So on this bottom part, after all of each of the exceptions, I would like you to add H plus to each of those lists of exceptions. Just on the bottom half, add H plus. So it would, the compounds of NH4 plus, the alkali metal cations, Ca2 plus, Sr2 plus, and Ba2 plus, and H plus. Do that for each of those on the bottom. Yeah, we'll talk. So just put H plus. And then I'll talk about how to use this chart. Okay, so in this class, acids start with H. They're going to be soluble. So what that means here, the way you read this is that the top part is anions, negative ions, that are generally soluble if they're in a compound, okay? So if you have a compound containing nitrate, it's going to be soluble, and there are no exceptions to that. That's what that means, that it's always going to be soluble. Same with acetate. Compounds containing acetate, so sodium acetate, magnesium acetate, are going to be soluble, no exceptions. You move one line down and you have chloride, Cl-. It's going to be usually soluble except when it's with silver, mercury, or lead 2+. Okay? So what you would say is if it were something like NaCl, it would be soluble, so it would be aqueous. However, if it's AgCl, it's going to be insoluble, so it's solid. Okay, so insoluble, soluble except for if it's with these guys. The bottom part is the opposite. These are ions that are generally insoluble. However, when they're with these guys, they tend to be soluble. Okay? The rules that you have to memorize, you won't have to memorize the exceptions, but you have to memorize that nitrate, acetate, ammonium, and group 1A, which is H plus and all the alkali metals, are always soluble. You'll have to know that for the test. Okay? Any questions on how to use this chart? Let's do our worksheet.